The Geiger-Müller tube or GM tube is the sensing element of the Geiger counter instrument used for the detection of ionizing radiation. It was named after Hans Geiger, who invented the principle in 1908, and Walther Müller, who collaborated with Geiger in developing the technique further in 1928 to produce a practical tube that could detect a number of different radiation types. It is a gaseous ionization detector and uses the Townsend avalanche phenomenon to produce an easily detectable electronic pulse from as little as a single ionizing event due to a radiation particle. It is used for the detection of gamma radiation, X-rays, and alpha and beta particles. It can also be adapted to detect neutrons. The tube operates in the Geiger region of ion pair generation. This is shown on the accompanying plot for gaseous detectors showing ion current against applied voltage. Whilst it is a robust and inexpensive detector, the GM is unable to measure high radiation rates efficiently, has a finite life in high radiation areas, and is unable to measure incident radiation energy. So no spectral information can be generated, and there is no discrimination between radiation type. Principle of operation. The tube consists of a chamber filled with an inert gas at low pressure. The chamber contains two electrodes, between which there is a potential difference of several hundred volts. The walls of the tube are either metal or have their inside surface coated with a conductor to form the cathode, while the anode is a wire in the center of the chamber. When ionizing radiation strikes the tube, some molecules of the fill gas are ionized, either directly by the incident radiation or indirectly by means of secondary electrons produced in the walls of the tube. This creates positively charged ions and electrons, known as ion pairs, in the fill gas. The strong electric field created by the tube's electrodes accelerates the positive ions towards the cathode and the electrons towards the anode. Close to the anode in the avalanche region, the electrons gain sufficient energy to ionize additional gas molecules and create a large number of electron avalanches which spread along the anode and effectively throughout the avalanche region. This is the gas multiplication effect, which gives the tube its key characteristic of being able to produce a significant output pulse from a single ionizing event. If there were to be only one avalanche per original ionizing event, then the number of excited molecules would be in the order of 106 to 108. However, the production of multiple avalanches results in an increased multiplication factor which can produce 109 to 1010 ion pairs. The creation of multiple avalanches is due to the production of UV photons in the original avalanche, which are not affected by the electric field and move laterally to the axis of the anode to instigate further ionizing events by collision with gas molecules. These collisions produce further avalanches, which in turn produce more photons, and thereby more avalanches in a chain reaction which spreads laterally through the fill gas, and envelops the anode wire. The accompanying diagram shows this graphically. The speed of propagation of the avalanches is typically 2 to 4 cm per microsecond, so that for common sizes of tubes the complete ionization of the gas around the anode takes just a few microseconds. This short, intense pulse of current can be measured as a count event in the form of a voltage pulse developed across an external electrical resistor. This can be in the order of volts, thus making further electronic processing simple. The discharge is terminated by the collective effect of the positive ions created by the avalanches. These ions have lower mobility than the free electrons due to their higher mass and remain in the area of the anode wire. This creates a space charge, which counteracts the electric field which is necessary for continued avalanche generation. For a particular tube geometry and operating voltage, this termination always occurs when a certain number of avalanches have been created. Therefore, the pulses from the tube are always of the same magnitude regardless of the energy of the initiating particle. Consequently, There is no radiation energy information in the pulses, which means the Geiger-Müller tube cannot be used to generate spectral information about the incident radiation. Pressure of the fill gas is important in the generation of avalanches. Too low a pressure and the efficiency of interaction with incident radiation is reduced. Too high a pressure, and the mean free path for collisions between accelerated electrons and the fill gas is too small, and the electrons cannot gather enough energy between each collision to cause ionization of the gas. The energy gained by electrons is proportional to the ratio E-P, where E is the electric field strength at that point in the gas, and P is the gas pressure. Types of tube. Broadly, there are two main types of Geiger tube construction: end-window type for alpha particles, low-energy beta particles, and low-energy X-rays. The usual form is a cylindrical end-window tube. This type has a window at one end covered in a thin material through which low-penetrating radiation can easily pass. Mica is a commonly used material due to its low mass per unit area. The other end houses the electrical connection to the anode. Pancake tube. The pancake tube is a variant of the end-window tube, but which is designed for use for alpha and beta contamination monitoring. It has roughly the same sensitivity to particles as the end-window type, but has a flat annular shape, so the largest window area can be utilized with a minimum of gas space. Like the cylindrical end-window tube, mica is a commonly used window material due to its low mass per unit area. The anode is normally multi-wired in concentric circles, so it extends fully throughout the gas space. Windowless type. This general type is distinct from the dedicated end-window type, but has two main subtypes, which use different radiation interaction mechanisms to obtain a count. Thick-walled, used for high-energy gamma detection. This type generally has an overall wall thickness of about 1 to 2 mm of chrome steel. Because most high-energy gamma photons will pass through the low-density fill gas without interacting, the tube uses the interaction of photons on the molecules of the wall material to produce high-energy secondary electrons within the wall. Some of these electrons are produced close enough to the inner wall of the tube to escape into the fill gas. As soon as this happens, the electron drifts to the anode and an electron avalanche occurs, as though the free electron had been created within the gas. The avalanche is a secondary effect of a process that starts within the tube wall. The avalanche is not the effect of radiation directly on the gas itself. Thin-walled tubes are used for high-energy beta detection, where the beta enters via the side of the tube and interacts directly with the gas. But the radiation has to be energetic enough to penetrate the tube wall. Low-energy beta, which would penetrate an end window, would be stopped by the tube wall. Low-energy gamma and X-ray detection. The lower-energy photons interact better with the fill gas, so this design concentrates on increasing the volume of the fill gas by using a long thin-walled tube and does not use the interaction of photons in the tube wall. The transition from thin-walled to thick-walled design takes place at the 300 to 400 keV energy levels. Above these levels, thick-wall designs are used, and beneath these levels the direct gas ionization effect is predominant. Neutron detectors. GM tubes will not detect neutrons since these do not ionize the gas. However, neutron-sensitive tubes can be produced which either have the inside of the tube coated with boron, or the tube contains boron trifluoride or helium-3 as the fill gas. The neutrons interact with the boron nuclei, producing alpha particles, or directly with the helium-3 nuclei, producing hydrogen and tritium ions and electrons. These charged particles then trigger the normal avalanche process. Gas mixtures. The main component is an inert gas such as helium, argon or neon, in some cases in a Penning mixture, and a quench gas of 5 to 10% of an organic vapor or a halogen gas to prevent multiple pulsing. The halogen GM tube was invented by Sidney H. Leibson in 1947. The halogen tube discharge mechanism takes advantage of a metastable state of the inert gas atom to more readily ionize a halogen molecule than an organic vapor, enabling the tube to operate at much lower voltages, typically 400 to 600 volts instead of 900–1200 volts. This type of GM tube is therefore by far the most common form now. It has a longer life than tubes quenched with organic compounds, because the halogen ions can recombine while the organic vapor is gradually destroyed by the discharge process. Geiger plateau. The Geiger plateau is the voltage range in which the Geiger counter operates. If a GM tube is exposed to a steady radiation source and the applied voltage is increased from zero, it follows the plot of ion current shown in the lead section of this article. In the Geiger region, the gradient flattens. This is effectively the Geiger plateau. Depending on the characteristics of the specific tube, the exact voltage range of the plateau will vary. In this plateau region, the potential difference in the counter is strong enough to allow the creation of multiple avalanches. Below the plateau, the voltage is not high enough to cause complete discharge, and individual Townsend avalanches are the result. The tube acts as a proportional counter. If the applied voltage is higher than the plateaus, a continuous glow discharge is formed and the tube cannot detect radiation. It is normal to operate the tube in the middle of the plateau so that variations in the voltage of the tube do not take it out of the Geiger operating region. The plateau has a slight slope caused by increased sensitivity to low-energy radiation, due to the increased voltage on the device. Normally when a particle enters the tube and ionizes one of the gas atoms, complete ionization of the gas occurs. Once a low-energy particle enters the counter, it is possible that the kinetic energy in addition to the potential energy of the voltage are insufficient for the additional ionization to occur, and thus the ion recombines. At higher voltages, the threshold for the minimum radiation level drops, thus the counter's sensitivity rises. The counting rate for a given radiation source varies slightly as the applied voltage is varied. For standardization of the response of the instrument, a regulated voltage is used to maintain stable counting characteristics, quenching and dead time. The ideal GM tube should produce a single pulse on entry of a single ionizing particle. It must not give any spurious pulses, and must recover quickly to the passive state. Unfortunately for these requirements, when positive argon ions reach the cathode and become neutral argon atoms again by obtaining electrons from it, the atoms can acquire their electrons in enhanced energy levels. These atoms then return to their ground state by emitting photons, which can in turn produce further ionization and hence cause spurious secondary pulse discharges. If nothing were done to counteract it, ionization could even escalate, causing a so-called current avalanche, which if prolonged could damage the tube. Some form of quenching of the ionization is therefore essential. The disadvantage of quenching is that for a short time after a discharge pulse has occurred, the tube is rendered insensitive and is thus temporarily unable to detect the arrival of any new ionizing particle. This effectively causes a loss of counts at sufficiently high count rates and limits the GM tube to a count rate of between 104 to 105 counts per second, depending on its characteristic. A consequence of this is that ion chamber instruments are preferred for higher count rates. External quenching uses control electronics to temporarily remove the high voltage between the electrodes after each discharge. Self-quenching or internal quenching tubes stop the discharge without external assistance, by means of the addition of a small amount of a polyatomic organic vapor such as butane or ethanol, or alternatively a halogen such as bromine or chlorine. If a poor diatomic gas quencher were introduced to the tube, the positive argon ions, during their motion toward the cathode, would have multiple collisions with the quencher gas molecules and transfer their charge and some energy to them. Neutral argon atoms would then be produced and the quencher gas ions would reach the cathode instead, gain electrons in excited states which would decay by photon emission, thereby producing spurious tube discharge as before. However, effective quencher molecules, when excited, do not lose their energy by photon emission but by dissociation into neutral quencher atoms. No spurious output pulses are then produced. Fold back. One consequence of the dead time effect is the possibility of a high count rate continually triggering the tube before the recovery time has elapsed. This may produce pulses too small for the counting electronics to detect and lead to the very undesirable situation whereby a GM counter in a very high radiation field is falsely indicating a low level. This phenomenon is known as fold back. An industry rule of thumb is that the discriminator circuit receiving the output from the tube should detect down to 1/10 of the magnitude of a normal pulse to guard against this. Additionally, the circuit should detect when pulse pile-up has occurred, where the apparent anode voltage has moved to a new DC level through the combination of high pulse count and noise. The electronic design of Geiger-Müller counters should be able to detect this situation and give an alarm. Detection efficiency. The efficiency of detection of a GM tube varies with the type of incident radiation. Tubes with thin-end windows have very high efficiencies for high-energy beta, though this drops off as the beta energy decreases due to attenuation by the window material. Alpha particles are also attenuated by the window. As alpha particles have a maximum range of less than 50 mm in air, the detection window should be as close as possible to the source of radiation. The attenuation of the window adds to the attenuation of air, so the window should have a density as low as 1.5 to 2.0 mg per square centimeter to give an acceptable level of detection efficiency. The article on stopping power explains in more detail the ranges for particles types of various energies. The counting efficiency of photon radiation depends on the efficiency of radiation interaction in the tube wall, which increases with the atomic number of the wall material. Chromium ion is a commonly used material, which gives an efficiency of about 1% over a wide range of energies. Energy compensation. If a GM tube is to be used for gamma or X-ray dosimetry measurements, the energy of incident radiation, which affects the ionizing effect, must be taken into account. However, individual pulses from a GM tube do not carry any energy information. A solution is to assign a radiation dose to each counting event, so the tube characteristic relates the number of counts to the intensity of incident radiation. At low photon energy levels, the response increases as low-energy photons have a greater interaction with the fill gas than high-energy photons. The tube therefore has an increased response for radiation which has a lower dose rate, and a correction must be applied to prevent an incorrect high reading for low-energy photons. This discrepancy can be 2 to 3 times greater or more, and for a thick-walled tube usually peaks at about 60 keV, where radiation interactions with the gas are still large, but the shielding effect of the wall has not become dominant. This correction is achieved by energy compensation of the tube, which modifies the number of count events in accordance with the energy of the incident radiation by using an external filter collar of energy absorbing material. The collar has an increased attenuation of low-energy gamma, and so compensates for the increased energy response of the naked tube at those levels. The aim is that sensitivity, energy characteristic of the tube should be matched by the absorption, energy characteristic of the filter. This results in a more uniform response over the stated range of detection energies for the tube. Lead and tin are commonly used materials, and a simple filter effective above 150 keV can be made using a continuous collar along the length of the tube. However, at lower energy levels this attenuation can become too great. so air gaps are left in the collar to allow low-energy radiation to have a greater effect. In practice, compensation filter design is an empirical compromise to produce an acceptably uniform response, and a number of different materials and geometries are used to obtain the required correction.